Lecture AP 1.8. This one's about balancing redox reactions. Specifically, it's ones that are in basic environments. We did in class today, I believe 1, 2, and 3, and these were in acidic environments. So we're working on number 4 and 5 for work of home tonight. And you certainly could try number 4 right now and give your best effort, but I think I did give you the rules, okay, for a basic environment rather quickly. So I'd like to show you how I would go about, let's say, balancing number 4, and maybe I'll give you the solutions for number 5 in terms of me going through them in a more faster way, and you can work on them yourself. So let me model number 4 for you. Okay, and they undergo the same rules if you're in a basic environment. So here we are in a basic environment. So we're going to do the same steps as we did before, but now we're going to do, there's an extra little twist at the end that gives these reactions a little more to think about if it's in a basic environment. But in any case, 95% is the same, so this is a good review in any case. So let's get started, as we would say in New England. All right, so I'm going to do this a little differently today. I'm going to write in steps how this changes, okay? So I'm going to keep my two half reactions a little bit separate, and so we'll follow along, see what works. Hopefully no doohickeys. Any case, here we go. So I'm going to start with Cn negative, and I'm going to go to Cn 0. I'm looking at a net ionic equation, and this equation is giving, it's missing the protons or the water. We don't know if there is overall, but that's the net ion. Any case, moving on. So what's happening here? We're going to balance everything other than the oxygens. Here's a carbon, carbon, N, missing an O. So I'm going to add an O to this side by adding water. We balance oxygens by adding water. Now, of course, by doing that, we are unbalancing this side of the reaction with hydrogens. So I need 2 protons. Even though we're in a basic environment, I'm still following my same rules as if I was in an acidic environment. Okay, so I put the 2 protons there. All right. So we balanced their H's, we balanced their O's, okay, and now we've got to balance the charge. Okay, now this is where it's different, okay, because now I'm just going to change inks here. Now we're going to add, at this point, if this was an acidic solution, I'd add electrons so that both sides of a half reaction have the same charge. But dealing with this proton here, it's a basic solution. So what's different at this point, okay, is that we're going to add hydroxides. And I'm going to add as many hydroxides as I need to neutralize, okay, the half reaction, or this reaction here. So I'm going to add 2 hydroxides. And what I add to one side, I'm going to add to another. Since I'm in a basic environment, I can clearly do that. So we're adding hydroxides to both sides. Now, what does that do to my equation? I'm going to rewrite it again. Okay, well, I'm going to have 2 hydroxides plus my water plus the cyanide ion plus this ion. I don't know the name of it. It might be a cyanate. I'm not really sure. Okay. And then what we're going to do here is 2 protons and 2 waters. The reason that I added 2 hydroxide was to completely neutralize the protons. So in any case, this would become 2 waters. So 2 protons, 2 hydroxide makes 2 waters. And now I'm at the point now where I can now look at charge. So essentially all I did was add hydroxides. That was determined by how many protons I had. Okay, I neutralized to make water, but you have to remember, if I'm adding hydroxides to one side, I have to add hydroxides to the other to maintain the law of conservation of mass. Okay, we added the waters initially to balance off the oxygens and the hydrogens, protons, because of the extra hydrogen. So this is still the same idea here. Okay, so now we're going to have to add some electrons. Now before I do that though, I see that there is some things to balance. I know, or I can cancel off. I notice there's a water, okay, on this side, and there's 2 waters on this side. So I can clean this up a little bit. Now I'm going to rewrite it one more time. Okay, and it's going to be 2 hydroxides, okay, plus the cyanide ion because I just lost the water, okay, plus this ion, and I lost one of the waters, right? Because I canceled off one of the waters, so this becomes just H2O. All right, understanding that if I'm making 2 waters and I'm starting with 1, there's an overall production of 1 water. You could have left it and you wind up canceling later. It doesn't really matter. I'm going to clean it up as much as I can to start with, okay, when I get the opportunity. So in any case, now I got a balanced charge. Okay, I have a -3 on this side. All right, look at your total charge, -3. And of course, this side, I have a -1. Don't know why my voice went up, but hey. So to balance off this half reaction, I need 2 more negatives on this side of the half reaction to make both sides equal to -3. Remember, we're balancing charge. We're also balancing mass, and the charge part is due to the electrons not being destroyed nor created. In any case, we put 2 electrons, 2e -1, and that gives me the same charge on both sides, which is now -3. So that's your check. Your check is to make sure that in your half reaction you have the same charge, and I think I do. -3, and then -1 plus a -2, -3. So this is my finished half reaction, okay, for the first one. And I'll just put, all right, we have that there. So the big fill-in arrow, okay. All right, I'm going to start again, just keeping things, I don't know, changing up. Now I dealt with the cyanide ion. I dealt with the permanganate ion. Permanganate is per because there's MnO, MnO2, MnO3, MnO4. So the perm is the greatest number, MnO4. Any case, so here we go. We're going to take the MnO4. It's -1. It becomes MnO2. All right. What am I looking at? Well, I'm looking at negative and a positive, but more importantly, I have one Mn and I have another manganese. So that's okay, but the oxygens are not balanced, so I have to add 2 waters here. Okay, that gives me the 4 oxygens on both sides. However, now I have 4 protons that go on this side. And if I was balancing in an acidic environment, I would stop here and balance my total charge with electrons and move on. But I do not, because I have to, okay, add how many hydroxides to neutralize? Yeah, you said it. You go, guy and girl. Okay, you said it. Maybe you didn't, but it'll be 4 hydroxides you're adding. And what you add to one side of an equation, you're adding to another. We have excess hydroxides to do that because it's, of course, in a basic solution again. Now what happens? I'm going to rewrite this. The 4 hydroxides and 4 protons, of course, makes 4 waters. Of course, I still have the permanganate ion. Okay, the manganese dioxide doesn't change. And of course, I'm adding 2 waters. Plus, again, the 4 hydroxides. Nothing changes over here. Okay, so now I'm going to, in this half reaction, I'm going to have to now, at this point, balance the charge. On this side, we have a -1. On this side, we have a -4 because of the 4 hydroxides. So clearly, I need 3 more negatives on this side so that each half reaction, or this half reaction, has the same charge on both sides. So I'm going to add 3 electrons. Okay, let me erase some of this stuff, and I'm going to rewrite it. No, I'm good. I don't think I'll write it anymore. Okay, so that is my half reaction. Okay, now I am going to get rid of this middle one here. And I'm going to get rid of all the rest of this so we can clearly see what we're working with. Obviously, if you need to see it, you can rewind the video. Okay, any case, moving on. So these are my half reactions. Okay, notice the problem here is that the MnO4, the permanganate ion, is accepting 3 electrons from the cyanide who's giving off 2. And the problem that we have, obviously, is that there's an unequal number of electrons through these 2 half reactions. Cyanide's giving off 2, permanganate is accepting 3. Right now we're not balanced by charge because, of course, we're missing an electron somewhere. Can't do that. We have to balance our electrons. So that both half reactions have the same number of electrons going into the reaction and leaving the reaction to have conservation of charge, we're going to multiply and distribute everything by 3 here. So I'm going to distribute the 3. The reason why I'm doing that is because I'm going to make this 6 electrons, and I'm going to just rewrite this. 3 times 1 H2O, that's going to be 3 waters. Then, of course, 3 of this ion. Of course, 3 cyanide ions. And, of course, 6 hydroxides. And that's what I get by doing the net ionic. I'm sorry, by multiplying by 3. Okay, now I'm going to multiply this other one by 2. Why? Because common factor is 6. So this gives me 6 electrons. Just going to rewrite it. 2 times 4 is 8 waters. And then 2 times 1 of the permanganate ions is 2. And when you're rewriting, make sure you don't forget the charges, because that could change everything. Okay, and then we have 2 times of the manganese dioxide. 2 times 2 is 4 waters, plus 8 hydroxides. All right, if I did that right, I'm just checking. And I did that right. Okay, so that is by looking at those two. And now I'm going to get rid of some other stuff here. Okay, so now we're looking at our final 2 half reactions. So these are the correct half reactions for the net ionic above. Okay, and let's see if everything cancels. Now we're just going to put this all together and cancel. We know that we're ready to do this because we see that we have the same number of electrons on both sides. We're absorbing 6 and we're losing 6, so now that we know this is the right way to do business here. That's your check. All right, so let's see what we have here. We have 6 hydroxides on this side. We produce 8, so I'm going to lose all the 6 and I'm left with 2, right? You're starting with 6 and you produce 8, there's a net change of 2, so that's how that works. Okay, I have a total of, don't forget, you have a total of 7 waters. Okay, a total of 8 waters. Okay, so I'm going to lose all my waters here, and I'm left with a total net of 1 water. I'm just going to write that so I remember. So I'm left with a water. Okay, and I'm left with 2 hydroxides over here. Okay, what else can cancel? I think nothing else. Okay, so we're canceling, or we're partial canceling the extra, so to speak, here by the waters and the hydroxides. And of course we have the 3 cyanide ions. Oops, there's a doohickey. Sorry. So we have the 3 cyanide ions plus, it's just kind of running out of space here. 3 cyanide ions, and then of course we have the 2 permanganate ions, MnO4, plus the water. I think I got everybody, right? 3 cyanide, the 1 water left, 2 permanganates, right? Other side of the arrow, we have the 3 Cn, oh yeah, mistake. We have 3 Cn0 negative plus the 2 manganese dioxide. And certainly this isn't difficult. It's definitely cumbersome and a lot of bookkeeping here. And you'll see a lot of these types of questions in a redox section of your test. They just love to make people balance redox reactions. Very difficult to balance these, because to figure out how many hydroxides or protons, if it's an acid, you just can't think about it. You can't think that way. Old school, you're going to have to go and do this type of balancing. You can't work it out in your head like you would do a very simple balancing, as I talked about today. Any case, so that's your balanced reaction. Now, what I forgot to mention today in class is that you could actually check this to see if it's correct. I'm not sure if I did that in class today. One way to check to see if it's correct is to see if the charge balances. Okay, so let's look at this. Okay, you have -2, okay, plus a -3, so I got -5 on this side. Okay, and then I have 3 times -1 is -3, plus 2 individual hydroxides that are -1, so that's a -5 also. So this tells me that I have balanced my mass and my charge. You certainly can go through and see how many carbons are in both sides, and you can do that as well. But a real fast check is to see, hey, if the charge is balanced, my redox reaction is balanced, and of course that works because you balance the electrons. All right, and that's how you do it. We did the same thing in class today, except what we did was, in today's part of today's lecture tonight, in any case, is we added the hydroxides, okay, after, okay, we added the protons. So once you add the protons to balance the H's that came from the extra waters or so forth, we add the hydroxides to neutralize the protons. You have to add them to both sides, and everything else is the same. So hope this helped. Please try number 5. I have the key of this on the website. Okay, I don't want to make this any longer than it has to. Ooh, we didn't answer a couple of things. Who's the oxidizer? Who's the reducer? Okay, no big deal. Who's the oxidizer? The oxidizer is the one that's the oxidizing agent, although I didn't spell that very well. It looks like oxidixer. Okay, that doesn't work very well. It's like elixir or something. So oxidizer is the one who is the oxidizing agent who forced oxidation, so therefore itself got reduced. Okay, it's the permanganate, I'm sorry, who got itself got reduced is the permanganate ion. So yes, it's MnO4, negative. Okay, we're not picking out the Mn, which is +7. We're pulling out the entire molecule. The reducer is the one that actually got oxidized, that lost the electrons, and that's the cyanide ion. Okay, and that's how that works. So I can see this is the oxidation half reaction. This is the reduction half reaction. Oxidation, how do I know? I'm losing charge. If I want to do the individual carbons, I could do that. Okay, and you can work that way, but that's as easy as you do. So we always pick the chemicals who are on, of course, all right, the reactant side for answers, because this is what's doing, these are the reactants, and this, of course, on this side is what's after the reaction has occurred. So those are the two principal agents we're looking for, and it should be clear who the oxidizer is, especially after I told you the structure today. It's very important you understand that you can pick out the permanganates is the oxidizing agent of the oxidizer, the Mn being in the middle and 4 O's surrounding it, pulling its electrons away, making it more positive than it is. It's +7, okay, but that +7 is basically stretched a little more because of these oxygens pulling its charge away, so it exposes the Mn, and of course it's a terrific electron sink to yank away from things. So that's what makes it, and again, it should be easy to identify that. Okay, so hope you enjoyed that, hope that worked for you, and please try number 5, doing the same things that we just did, and in the basic environment. If you're having problems, which I doubt, you certainly could take that three-page worksheet that I wrote out every single step to how to do things. Okay, bye-bye.